All right, all right. Hey everybody, we're going to continue with the Python learning streams. Remember that you can. This is for learning along, all together. Something in this case we're learning Pytorch. So if you have any questions, ask them. Without further ado, we're going to start. In the previous one, I got to do the tensor tutorial, a gentle introduction to the torch autograd function, and an introduction to neural networks. Now we're going to go and see training a classifier. And maybe we can do something else, the next one in this series. But yeah. So to continue this, we have here a training classifier. So we're going to print this. That's it. You have seen how to define neural networks, compute loss, and make updates to the weight of the network. Now you might be thinking, but what about data? Generally, when you have to deal with image, text, audio, or video data, you can use standard Python packages that load data into NumPy arrays. Then you can convert this array into a torch tensor. For images, packages such as Pillow, OpenCV are useful. For audio, packages such as SciPy and Librosa. For text, either raw Python or Python base loading, or NLTK and Spacey are useful. Alright. Especially for vision, we have created a package called Torch Vision that has data loaders for common datasets such as ImageNet, Cypher10, MNIST, etc. And transformers for images. Visualization, Torch Vision dataset, and Torch Utils data loader. This provides a huge convenience and avoids writing boilerplate code. For this tutorial, we will use the Cypher10 dataset. It has the classes, well, these ones. The images in Cypher10 are size 3 by 32 by 32, 3 channel color images of 32 by 32 pixels in size. Okay, so what we can note here. Let's note this. Let's put a slash here, so there you go. Now we're going to have these images to train the classifier, and these are labeled. So, training an image classifier. We'll do the following steps in order. Load and normalize the Cypher10 training dataset using Torch Vision. Define a convolution network. Define a loss function. Train the network on the training data. Test the network on the test data. Sweet. Let's write that. So let's see. Let's put a breather here. Great. What? Oh. There you go. Alright, so using Torch Vision is extremely easy to load Cypher 10. So import Torch, import Torch Vision, import Torch Vision, transforms. There you go. Shift enter. I didn't start the VM, so it's going to take a while. The output of Torch Vision datasets are PIL images of range 0 to 1. We transform them to tensors of normalized range -1 to 1. What is this? No. If you're running on Windows and you get a broken pipe error, try setting the num worker of Torch. Blah blah blah. Alright, we're not doing that. Great. Now let's do what it says. So I'm going to define the transforms. Do compose. So this is for creating a multiple set. Alright. We start with transforms to tensor, then normalize, great. Now train set Torch Vision the datasets C410 root data. What is it's weird. Train true, download true, and transform. All right. Then we have the train loader. Search utils data train set. Here we define the batch size to train. Right. Oops. Shuffle. True. Workers put 2. Great. Now we do this, but for the test set that is the same. All right. I think we don't gain anything for repeating this, so I'm going to so train is equal to false. Don't want here's test set and test other. Great. All right, now the classes. Again, we don't gain anything for typing this. Sometimes we do, sometimes we don't do. What did I miss? Here. Great. Let us show some of the training images for fun. Alright, so let's use the matplotlib. Awesome. Alright. So this function is for showing the images. Pretty easy. Or very simple, I should say. It's never easy. One, two, 0, and 3. This show. So let's see. Here we denormalize the image. We put it in the NumPy. We convert it to NumPy, I should say. And then we transpose the image to be the right direction. And we show it. Awesome. Data iter. Alright. Images, labels, iter, next. I'm not that familiar with iterators, but I think that when you ask for the next, what happened? You can ask for the next one, and it is going to give you the next in the list, I think. So here we grab the 2 first images of the dataset. Alright, so these images is a batch, so it's going to have multiple images with this util with this utils function. We make a grid and we show the image, and we can print the labels also. Let's do that. So here we join. Kind of weird doing that. I think there is a better way of doing this, but for now let's copy this. Never used this, to be honest. I always use the F and the string. And range is an inline for loop. 2, 3. And let's see if you had a typo or not. Okay, have a typo in the first line. Awesome. Great. And here we have our 4 images: deer, sheep, and a bird. Great. It's different from this because we shuffle here. So this is random. Awesome. Now let's do Convolutional neural network. Sweet. No, I didn't want that. We keep it. We don't. All right. So let's create this CNN. Copy the neural network from the neural network section before and modify it to take 3 channels images instead of 1 channel images as was defined. Oh shit, sorry. Import torch nn as nn, import torch and then functional as functional. Class network is an NN module. What? I think this is for extending the class, right? Extending the module class. Super. Great. So here we're going to have the first layer with a convolution of, let me remember what that was. 3 channel, 6 filters, and 5 outputs, something like that. Let's check. I think that here, input channel, output channel, and kernel size. So the output channel is going to have 6 and kernel size of 5. Great. All right. Then we have the pool. The max pool. And then we repeat with another convolution. Awesome. And now 3 layers of fully connected layers or linear layers. (16 by 5 by 5). All right. So let's see why this. I'm thinking it was explained before, but didn't quite no. Well, I need to research this because it's pretty important. 16 by 5, so there's these 2 and another 5. I don't know. For now, let's leave it at that. Another fully convolutional. Fully connected, I wanted to say. The third one, 84 and 10. Great. Now let's put it all together with the forward method. So we have the X self the pool. I don't quite know what this one does, honestly. Let's search it. Oh, silly me. Pool is this one. Alright, never mind, never mind. Let us continue review and the first convolutional with the input. Then we go to the next one, pull, a value, and a second convolution. Now we arrange the tensor in another direction. Wait, I remember. Or is it for doing like a flat? I think here we are flattening the tensor x. We pass it through the first fully convolutional, then to the second one, and finally to the third one without the value. Great, let's see if I read it correctly. I think I did. Here we instantiate the network. Alright, didn't have any errors, I think. So now let's move on to define a loss function and optimizer. Define loss function and shoot. Alright. Import Pytorch.optim. Now the criterion, that word doesn't make sense. I don't know. Let's write a CNL cross entropy shoot gross entropy loss optimizer. Yeah. Google is scaring me. In a moment we are going to use that. Don't worry. Optim stochastic gradient descent with the network parameters, a lightning rate of 0.001 and a momentum of 0.9. Sweet. And it's as easy as that, isn't it? We're going to train the network. This is when things start to get interesting. We simply have to loop over our data iterator and feed the inputs to the network and optimize. Awesome. Let's really focus on this to understand this part, because as the text says, it's the most interesting part. So for each epoch in the range of 2, so we're going to do 2 epochs. Running loss. It's maybe for keeping track and logging. So for I, data in enumerate train loader and 0. Let's remember what the train loader was. So train loader was this one. And we saw here that when we retrieve this, we have images and labels. And here we grab the eye that is going to have that's going to have the image and the label and the data starting from 0. See that, right? So here we get the inputs. Data is a list of inputs and labels. Or it was the other way around. So we have inputs and the labels in the data. The screen protector is going to change the color of the screen, so we're going to shut it down. All right, there you go. All right, so so first we set the gradients. Then we grab the output of the network. Let's see here. We calculate the loss. We change it to cell. Outputs and labels. Then so this one was for calculating the gradients of the loss function and putting that gradient into the network parameters, a special variable called grad, right? And then we call optimizer.step to update all of those parameters for the amount of that gradient. Awesome. Now, statistics. Print the statistics running. Score loss equals to plus item. All right. Loss item for grabbing the loss value. If I mod 2000 equals to 199. Is that the mod or division? I don't know. Doesn't really matter. This is a little bit of a mess, so I'm going to copy this. Right. Running loss equal to $0. And finally, finish print finish set training. Okay, so shift enter and let's hope I didn't. I did. And that's that. Hope this doesn't take that long. Well, it's going to take a while. How many it was? I think he had like 70,000 or something like that. Maybe it's the smaller one that had 10k. Well, let's see. 12,000. He had 12,000. Right. Well, that it's running. Let's do the next thing. That is, let's quickly save the model. So I'm going to choose a path. It doesn't really matter in collab, but let's do anyway. We could connect to Google Drive, but this is a toy model, so it doesn't really matter. All right. Just about there. Then we test the network and training on the GPU. We changed a couple of things to train the GPU. Okay, so this is training on the CPU. Interesting. We save the thingy. Now let's do test network on the test data. Okay, so we have trained the network for 2 passes over the training data set, but we need to check if the network has learned anything at all. We will check this by predicting the class label that the neural network outputs and checking it against the ground truth. If the prediction is correct, we add the sample to the list of correct predictions. First step, let us display an image for the test to get familiar. It ain't familiar. Same as before. On cap. Don't get anything by writing that, I think. Okay. Great. Next, let's load back in our save model. Note, saving and reloading the model wasn't necessary here. We only need to understand how to do so. Yes. So network load state dict. The same as saving, but here we load the state dict. It's for a dictionary, right? See if it works. Awesome. So now let us see when there outputs go to net images. And it says the outputs are energies energies for the 10 classes. I'm thinking because I think I read that it was probabilities, but I think in this case they don't want to say that, or maybe there's some other concept that I'm not familiar with. But if we go for energies, the higher the energy for a class, the more the net will think that the image is of the particular class. So let's get the index of the highest energy. So slash predicted touch max outputs on the first axis. Okay, I'm going to copy this. So frog, dog, and deer. You confuse the horse for a dog. Okay, fair enough. The result seems pretty good. Let us look at how the network performs on the whole data set. Alright, so we define the correct variable here, then the total, and Pytorch without the grading, so no grad. We grab the images and the label from the data. Then we generate the output of that batch. We calculate the max. So max of outputs data in the first axis. Then we add one. No. We add to the total the amount that's being predicted, and then the correct images. So if the predicted array is equal to the predicted labels, or the run through the labels, we sum that, and we grab. I don't know what this does though. Let's find out. It says returns the value of this tensor as a standard Python number. This only works for a tensor with one element. For other cases, see to list. This operator is not differentiable. Alright. Great. Great. Finally, we do print that. So we do $100 times correct divided by the total amount. I'm going to get a percentage, and I fucked that up. Predicted is not defined. Okay, it's going to take a while, I guess. I don't know. 56. Let's see if ours is better. It shouldn't, but that looks better. That looks way better than chance, which is 10% accuracy, randomly picking a class out of 10 classes. Seems like the knight will learn something. What are the classes that perform well and the classes that didn't perform well? 57. Ha! One more. Alright, so let's calculate what classes did better than the other. So we have class correct, go to list, BDB boom. So here we're creating a list of floats with 10 items, and we do the same with the total. Great. And we do the same with Torch no grad. For data in test loader, dimensions labels from the data. We calculate the outputs. And we grab the predicted going for the max of the outputs tensor. All right. Now the C thing here is that the predicted go to labels squeeze. So squeeze eliminates any extra dimension that is not being used. I think that was the use case for that. So for E in range 4 label, yeah, so for each image in the epoch, we put the label from the labels into his own variable, correct class, label. So here we access the correct class array into the ID of the class, and we put it there, right? We put this, but we sum that to the current value. Then we do this. We add 1 to the total of that label. All right. .SQL 1. Finally, we print that. Oh no, we need to do a for loop. Print that. Really, I never done this. Really. Let's change that because it's giving me. So let's use F. So here, if I'm correct, let's do accuracy. Let's make sure we typed correctly. Of the first thing here, classes I, and then we do all of this, right? Over here, like it makes it 2 digits, and this one 5 something. It doesn't really matter. Let's see. What did I do wrong? Okay. All right. Okay, so what's next? How do we run this neural network on the GPU and going to train on the GPU? Let's put this train on GPU. It keeps going. Keeps going. Let's read this then. All right, so pretty similar. Oh, this one is for like making it pretty. Okay, get it. It's sort of the same. Okay, so let's see how to make it train on GPU. Just like how you transfer a tensor onto the GPU, you transfer the neural network onto the GPU. Let's first define our device as the first visible CUDA device if you have CUDA enabled. Device, search device, CUDA. Okay. Nice. And I forgot. Print device. CUDA 0. So you can go NVIDIA SMI and see what you have. Polish. We have the P100 and we are doing like anything. I mean nothing. This is the most powerful GPU that Colab gives you. So that's cool. So the rest of this section assumes that device is a CUDA device. Then this method will recursively go over all modules and convert their parameters and buffers to CUDA tensors. So net to device. So you need to put the network on the GPU. Let's see how much it costs. So we have 10 megabytes before, and now we're going to have 800 megabytes. Holy sh! Didn't want that. So now remember that you will have to send the inputs and targets at every step to the GPU too. Why don't I notice a massive speed compared to CPU? Because your network is really small. Exercise tries increasing the width of your network arguments 2 of the first neural net convolutional layer and argument 1 of the second convolutional. They need to be the same number. See what kind of speed up we get. Goals achieved. And we achieved understanding the Pytorch tensor library and neural networks at high level, and train a small neural network to classify images. Great. But I'm going to test this. So let's go to the training and grab that and do what this says. So when we grab this, we need to grab the first one and say A to device, and grab the second one and we say A to device. All right, and then we run it. Let's see if we get a speed up or not. I'm not seeing anything yet. There you go. I mean, it's pretty the same, I think. Yeah, it's about the same. Well, all right. Let's do what the text suggests, that is to change the second argument, the output, and this one. So we're going to change this to, let's see, 64, a stack of layers, filters, a stack of filters. Let's stop this. Okay. And let's see, let's define this again. All right, then here where it was, I'm a little bit lost. Let's load it again. Oh, all right. Oh, that's right. Okay, doesn't matter. Let's do here. So network 2, and where we have the network here. Here we have. Let's put a better name, like, well, better name. Network 64. And put it to the network 64. So we instantiate the new network and we go again. Right? Oh, great. And network 64 to device. Let's see. Should be working now. Let's check this GPU has about the same. It's about the same. And the speed is about the same. Oh wait. No, it's good. All right. We're almost 1 hour, so I don't know. I got I had an hour for doing this, so oh, that's new. Notifications for the models. This. Go to the tutorials. Why is it doing that? Oh, that's right. The optimizer is not. Okay, I did whatever here. Pretty retired, to be honest. I had to define the optimizer again. What? What, what the optimizer wants? Oh, here. So yeah, because this is another network, so we are doing like, I don't know what we're doing here. So I don't think we need to import again, but doesn't matter. So yeah, we grab this and we change to optimizer 64 and the optimizer 64 and another to the 64, and let's see, this should be better. And this should be improving, right? I want a smaller one. So let's see what we can do. Alright, yes, I did an oopsie, but this is it. I'm going to end this section, and yeah, hope you like it. If you have any questions, comment below and subscribe to this channel.